This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. Imagine boosting your large language model inference throughput by 50% and slashing latency, specifically the 99th percentile time to first token, by a massive 70%. And achieving this not just by tweaking the model itself or the inference engine you're using, but by optimizing the underlying infrastructure, the plumbing, the orchestration, the system-level software that actually runs the models in the cloud. That's the promise of a new open-source framework called AIBrix, detailed in a recent paper, and its core innovation revolves around something called a distributed KV cache. We all know deploying open-source large language models, or LLMs, like Llama, Mistral, or DeepSeek, efficiently at scale is a huge challenge. You want the power and customizability of these open models, but you're constantly fighting against high operational costs, especially for GPUs, and frustratingly slow response times, known as latency. You might think, okay, I'll just use my standard cloud-native toolkit, Kubernetes, maybe some serverless frameworks like Knative, or even ML-specific serving tools like Kserve or Reserve. But here's the catch. These tools, powerful as they are for traditional stateless microservices, or even older machine learning models, weren't really built with the unique demands of large language models in mind. LLMs are different beasts. They're stateful, largely due to that crucial KV cache used during text generation. They process data token by token, not just request by request. Their resource needs, especially GPU memory for that KV cache, fluctuate wildly based on the length of the input prompt and the generated output. Standard tools often fall short in managing these specific characteristics effectively. This is where AIBrix steps in. It's presented as a cloud-native, open-source infrastructure framework specifically designed for large-scale LLM inference. The core philosophy behind AIBrix is something the authors call co-design. What does that mean in practice? It means that AIBrix isn't just about gluing together existing tools like Kubernetes, the distributed computing framework Ray, and an inference engine like the popular vLLM. Instead, it's different layers, the components that handle resource scheduling, autoscaling, request routing, and managing models across multiple nodes, are purpose-built to work seamlessly with the inference engine. They're designed to understand and optimize the specific interactions and resource needs of LLMs during inference. Think of it less like assembling generic components off the shelf and more like designing a high-performance engine and its control system together for peak efficiency. So how does AIBrix actually try to deliver on those performance promises? Let's dive into some of the key technical ideas presented in the paper. Perhaps the most eye-catching innovation is the distributed KV cache. First, a quick refresher. What's a KV cache? In transformer models, which underpin most LLMs, the attention mechanism needs to look back at previous tokens to generate the next one. To avoid recomputing the key and value representations for these past tokens every single time, inference engines store them in a cache, the KV cache. This cache is vital for efficient text generation, but it consumes a lot of precious GPU memory. Typically, this cache lives within a single inference engine instance on a single node. If you have multiple instances or nodes, each request usually builds its own cache or relies on limited caching local to that specific instance. AIBrix takes a different approach. It creates a distributed KV cache pool, potentially using DRAM across nodes that can be shared across different inference engine instances. Imagine a user interacting with a chatbot. The context of their conversation might be processed initially. With a distributed cache, subsequent turns of the conversation, even if handled by different server instances, could potentially reuse the cached keys and values from the shared pool. This avoids redundant computation, especially during the initial processing of the prompt, known as the prefill phase. The paper reports significant results from this. Comparing AIBrix's distributed cache combined with VLLM's built-in prefix caching against using VLLM's prefix caching alone, they observed a peak throughput boost of over 50% and a reduction in the 99th percentile time to first token latency, P99 TTFT, of around 70% on the BERT SQL benchmark. That's a massive improvement, potentially enabling much faster and more responsive interactive applications. Now, as engineers, you might be wondering about the potential downsides. Doesn't a distributed cache introduce its own overheads, like network traffic for moving cache entries or complexity in managing consistency? That's a valid concern. The AIBrix paper mentions specific optimizations to mitigate this. They describe using a, quote, scan-resistant eviction policy to be smarter about keeping frequently used cache entries available longer, reducing redundant data transfers. They also mention techniques like asynchronous metadata updates to minimize blocking operations, and even leveraging shared memory for faster data exchange when the cache service and the inference engine happen to be running on the same node. While the real-world network impact always depends on the deployment specifics, the design clearly anticipates and attempts to address these potential bottlenecks. Beyond the distributed cache, AIBrix incorporates several other optimizations tailored for LLMs. One is high-density LoRa management. LoRa, which stands for low-rank adaptation, is a popular technique for efficiently fine-tuning LLMs for specific tasks without retraining the entire massive model. This results in small adapter files, but serving potentially hundreds or thousands of these specialized fine-tuned model variants efficiently can be challenging. AIBrix allows for dynamic loading and unloading of these LoRa adapters within running inference server pods, enabling what the authors call high-density deployment. This means you could potentially serve many different fine-tuned models using fewer underlying base model instances, saving resources and costs, especially for less frequently requested long-tail models. It integrates with Kubernetes services for managing discovery and placement of these adapters. Then there's LLM-aware autoscaling. Traditional autoscalers in systems like Kubernetes, often configured via the horizontal pod autoscaler or HPA, or in frameworks like Knative, typically rely on metrics like queries per second, QPS, CPU, or memory utilization, or the number of concurrent requests. But for LLMs, these metrics don't paint the full picture. A single request with a long input prompt and requiring a long generated output can consume vastly more GPU resources, especially KV cache memory, than dozens of short requests. Scaling based purely on request count can lead to server instances getting overwhelmed before the scaler reacts, or scaling up unnecessarily when load is high in requests but low in computational demand. AIBrix implements auto-scaling policies that directly understand LLM-specific metrics, such as token processing throughput or, crucially, the actual KV cache memory utilization. It uses techniques like sliding window metric aggregation computed directly within the autoscaler component to get near real-time load information, bypassing potential delays common in standard metrics pipelines. The paper reports improvements like reduced latency and increased token throughput compared to standard Kubernetes HPA, along with fewer unnecessary scaling oscillations. Intelligently routing incoming requests is another area AIBrix focuses on. Standard load balancers might just use random or round-robin distribution. But again, LLMs have state. A particular server instance might already have the KV cache warmed up for a specific prompt prefix from a previous request. Or it might have more free GPU memory available to handle a large incoming request. AIBrix extends the popular Envoy proxy to act as an LLM-aware API gateway. It supports various routing strategies beyond simple load balancing. For example, a prefix cache-aware strategy attempts to send requests to instances that already have relevant KV cache entries, maximizing reuse and potentially speeding up the prefill stage. A least KV cache strategy routes requests to the instance with the most available KV cache memory, which might be better suited to accommodate requests needing large amounts of state storage. The paper claims these advanced routing strategies reduced mean latency by over 19% and 99th percentile latency by nearly 80% in their experiments, highlighting the significant impact of smarter, LLM-aware traffic management. For truly massive models, like the recently released Llama 3.1405B, which often don't fit on a single GPU or even a single machine, AIBrix proposes a hybrid multi-node orchestration approach. It uses Kubernetes for the coarse-grained resource management, things like provisioning the necessary nodes and managing the basic pod lifecycle. But it integrates Ray, a framework well-suited for distributed computing, to handle the fine-grained execution control and inter-process communication needed for techniques like tensor parallelism across multiple nodes. The authors argue this approach balances the production readiness and ecosystem of Kubernetes with the specific distributed execution strengths of Ray. This offers potentially more flexibility and better handling of service-oriented needs, such as performing rolling upgrades without downtime, compared to relying solely on the native distributed serving capabilities built into an inference engine like VLLM, which might prioritize raw parallelism over operational concerns. Now, let's talk about why this is particularly interesting for us as software engineers, especially when compared to existing solutions. The paper explicitly contrasts AIBrix with both traditional microservice frameworks like Knative and Istio and existing ML serving frameworks like Kserve and Rayserve. The core argument is that typical microservice tools often lack GPU awareness, and their fundamental concepts, like scaling based purely on request counts or employing complex service meshes like Istio, don't map well to the token-based, stateful, and GPU-intensive nature of LLMs. And while platforms like Kserve and Rayserve can certainly be used to deploy LLMs, the AIBrix authors argue they often lack the deep integration and specialized optimizations. AIBrix aims for things like the coordinated distributed KV cache, the fine-grained dynamic LoRa management, or the highly specific routing and autoscaling policies tuned for LLM behavior. This highlights the potential value proposition of a system truly co-designed for the unique challenges of LLM inference, rather than trying to adapt general-purpose tools. Another interesting feature described is SLO-driven heterogeneous serving. GPUs are expensive, and in reality, you might have a mix of different types available in your cluster, perhaps some powerful but costly newer GPUs, alongside some older or less powerful but cheaper ones, like maybe NVIDIA A10s and L20s as used in their example. Can you mix and match these intelligently to save costs while still meeting your performance targets defined by service-level objectives, or SLOs? AIBrix includes a GPU optimizer component designed to tackle this, based on analyzing workload characteristics, like typical input and output token counts, and using pre-deployment profiling data showing how different models perform on different GPU types. It attempts to determine the most cost-effective mix of GPU instances needed to handle the incoming traffic, while staying within defined latency SLOs. In an experiment mixing A10 and L20 GPUs, the paper reports achieving around a 10% cost reduction compared to using only the more powerful L20s, while accepting a slight latency increase up to 20% that remained within their target SLO. This kind of dynamic cost-performance trade-off optimization is highly relevant for production systems trying to manage budgets. However, the paper rightly points out limitations here. The evaluation was conducted under specific workload conditions, and the current reliance on offline profiling might be cumbersome for highly dynamic environments. How well this performs with less predictable, real-world traffic patterns is an area for future investigation. Finally, the paper also mentions AIBrix includes tools for AI accelerator diagnostics and failure simulation. These aim to help detect silent hardware errors or performance degradation in GPUs and allow engineers to test the fault tolerance of their deployment by simulating hardware failures, contributing to overall system reliability in production. So what's the takeaway for us as engineers? AIBrix presents a compelling vision for optimizing LLM inference infrastructure by tackling the problem holistically at the system orchestration level, going beyond just the model or the inference engine itself. The co-design philosophy, treating the infrastructure and the inference engine as tightly integrated partners specifically for LLM workloads, seems key. Innovations like the distributed KV cache demonstrate that potentially huge performance gains are still possible by rethinking fundamental assumptions about how state is managed during distributed inference. Of course, there are practical considerations. How mature is AIBrix today? It's presented as open source and clearly integrates several complex systems: Kubernetes, Ray, VLLM, Envoy, Deploying and managing such a stack in production undoubtedly requires operational expertise and effort. The paper mentions ongoing work and contributions back to related projects, like exploring extensions to the Kubernetes Gateway API specifically for inference workloads, which suggests active development and community engagement. The authors are also upfront about the limitations in their current evaluations, particularly around generalizing some results like routing and heterogeneous serving across diverse, unpredictable real-world workloads, which is typical for academic research introducing new systems. But the core idea remains powerful. If you're grappling with the cost and latency of serving open-source LLMs at scale, simply optimizing the model file or picking the fastest inference engine might not be the whole story. Looking deeper at how the entire system schedules resources, routes requests intelligently, manages critical state like the KV cache across instances, and handles operational aspects like efficiently serving fine-tuned adapters or utilizing mixed hardware resources, could unlock significant improvements. AIBrix offers one concrete, open-source approach to doing just that, built from the ground up with the unique challenges posed by these powerful but demanding language models in mind. It's definitely a project worth keeping an eye on for engineers working in the MLOPs and AI infrastructure space.